Hey guys, it's Iz. Today we're going to be talking about properties of gases. Sam and I collaborated on this project to provide you with all you need to know about this topic. So here are today's objectives that we are going to cover during today's lesson. We're going to understand the characteristics of gases. We're going to explain compression and diffusion. We are also going to learn the 4 different variables gases are measured with. So here are some questions you might want to think about while we learn about gases today. What are the properties all gases share in common, and why should we care? Also, how do gases differ from liquids and solids? By focusing on these questions, you'll get a better understanding about gases in general. To start, let's talk about the kinetic molecular theory. The kinetic molecular theory is a theory that states all matter is made up of atoms and molecules that are always moving. These particles hold kinetic energy and move around in random directions. So in higher temperatures, these particles have high energy, and in low temperatures, these particles have less energy. The more energy these particles have, the faster moving they are. Which makes sense, because think of a kid who has just eaten a lot of sugar. They have a tendency to be jumpy and more active and hyper. So if you can relate these particles to a child who has eaten a lot of sugar, you'll get a better understanding of how these particles move around. The first thing to understand of the kinetic molecular theory is that gases are very, very small particles. They are atoms, or they may even be molecules. Gases have a very large volume of space between them. So if you were to look at solids, liquids, and gases, you can see a solid because the particles are stuck very close together. It is also the same when you look at water, because the molecules stick together in a way that is visible. But if you look in front of you, there are probably a lot of things that are solid. But between you and the other solids is a gas. There are particles there in that gas, you just can't see them because the space between them is so large. There is literally nothing there, it's empty space. These gas particles aren't really attracted to each other nor are repulsed. Gases are also in constant random motion, meaning they're always moving around. They don't pick which path they're going to take. They're constantly moving all over the place. But when they do collide, we say these collisions are perfectly elastic. This means when they bump together, the energy is completely transferred without any loss. When measuring the temperature, you are really just measuring the kinetic energy. So if you heat something up, by increasing the heat, you are increasing the kinetic energy of the molecules. That means that they are moving faster. They are colliding more. So when you measure temperature, you're measuring how fast these molecules are really moving. Gases are easily compressible, and that's because of the high volume of space between particles that was number 1 in the kinetic molecular theory slide. Represented by the graphic, we see pressure being applied to the gas, and we notice that the molecules within the gas squish closer together. In regards to diffusion, it is the random movement of one gas through another, from a region of high concentration to a lower concentration. This movement does not rely on winds or air currents. An example of diffusion would be certain smells. As we see in the diagram, the smell is from rotting vegetables. There are 4 variables that describe gases, and they each correspond to a symbol that will be used in equations. When looking for temperature, you are looking for the capital T variable. With pressure, it is a capital P, for volume, a capital V, and despite what you might think, for amount, it is a lowercase n. In chemistry, we don't use degrees Fahrenheit, we use degrees Celsius, but in case of gases, we will use Kelvin, with an uppercase K. This is the one that we're going to use because it doesn't involve negatives. As far as pressure, it is measured in ATMs, which is atmosphere. You will also use millimeters mercury and also kilopascals. Amount symbol is variable n. It actually represents any time we use a mole. We know how to convert between moles and masses, so again, it is easy to convert through. Now let's take a look at the 4 basic properties of gases. While talking about the properties of gases, think of them in context of a balloon. Think of a balloon, and as you blow air into this balloon, you're adding molecules to the air. As more of the air gets added to the balloon, the volume is going to increase. Volume is proportional to the amount of gas, and for that to be true, we need a constant temperature and pressure. You may ask why. You'll see how temperature and pressure also affects the volume. The second property is pretty interesting. If the balloon has a fixed amount of air in it, or in other words, it has a string tied to the end, so you can't add or remove air, when heated, the balloon will expand. This also increases the volume. If the balloon was to be cooled, the volume would also decrease. So we can say volume changes directly with temperature when the pressure is constant. If you were to squeeze the balloon, the volume will decrease because it is compressing. So we can say the volume changes inversely with the pressure. If you're squeezing really hard, in other words, you have a lot of pressure, the volume is going to decrease. And for this to be true, the temperature has to be constant. Now, the fourth and final property of gas explains, if you fix the volume of the balloon and add more air, the pressure inside will increase. So the pressure changes directly with the amount of gas. This makes sense because if there's more molecules, they're jumping all around the place. That means more molecules are going to be hitting the sides of the balloon, increasing the pressure. That is, if the volume and temperature of the balloon is constant. Based on the properties we just covered, you should be able to complete these practice problems. So pause the video now and start working on them. In the first one, we see that the volume decreased. And as the third gas law states, volume changes inversely with pressure. So if the volume is decreasing, the pressure is going to be increasing. The second one goes back to the idea that when you increase the temperature, as we see 60 degrees Celsius to 100 degrees Celsius, we are also increasing the kinetic energy. So when we are increasing kinetic energy, we are giving the molecules more reason to move around and bounce around. When these molecules are moving and bouncing around, they are hitting the walls of the container. So we can say that because these molecules are rapidly and quickly hitting the walls of the container, the pressure is going to be increased. In the last problem, the amount of gas increased. So if we go to the last basic property, it states that pressure changes directly with the amount of gas. Since you can see visually that the amount has increased, we also know that the pressure increased as well. I hope you guys did well on that. We're now going to be moving on to how gases exert pressure, which is something that we focused on when we were doing the worksheet and when we were talking about the basic properties. Basically, the molecules are continually colliding with each other and with the walls of the container. When a molecule collides with the wall, they exert small force on the wall. The pressure exerted by the gas is due to the sum of all these collision forces. The more particles that hit the walls, the higher the pressure. That explains why when the amount increases, the pressure also increases. Now, what do we do with all this pressure? Why do we care? Well, there's something called atmospheric pressure. Atmospheric pressure is really the pressure of your atmosphere, just like it sounds. There are lots of air molecules like oxygen, nitrogen, helium, argon, and they are bouncing around hitting the surface of Earth and they are weighing down on you. So, if you've actually ever heard someone say they feel like it's going to storm, what happens is that in thunderstorms we usually end up with low pressure, which means that volume increases, as we already know. Sometimes people may have little bubbles of gas in their joints, and if the pressure drops, the little bubbles of gas expand. When they expand, they pinch different nerves, so it hurts. So literally, they can feel when it's going to storm, because the atmospheric pressure has gone down. With all the pressure units that you saw, we need to know how to convert between the one we are going to use most, which is atmosphere. It is represented with the label ATM. Obviously, there is no conversion to atmosphere, so there's a line through the conversion box. Millimeters of mercury is labeled mmHg. 1 atmosphere is equal to 760 millimeters of mercury. This is a crucial conversion to remember. The other one is kilopascals, which is represented by kPa. 1 ATM is equal to 101.3 kPa. Here are 2 practice problems that are going to get you started with converting pressure. So pause the video now and we'll go over the answers when you are done. We are going to be using STOIC like we did in the last unit. So to begin solving, you start with 1.15 ATM. And you know from the previous slide that there are 760 millimeters of mercury in 1 ATM. When you solve, you get 874 mmHg. For the next problem, we would start with 94.6 kPa. Since we don't have a straight conversion, we can go to ATMs first. 1 ATM is equal to 101.3 kPa, and to get to millimeters of mercury, we do a similar conversion to the first problem. And when we solve, we find out that it equals 710 mmHg. You're also going to see temperature conversions. Temperature conversions are one thing, pressure conversions are another. Celsius is what's easier for us to measure things in because that's usually what our temp probes are set up for. However, we are looking for Kelvin, so using this equation, we can find the desired temperature. This equation is fairly easy to use. We see that we have 17 degrees Celsius in the first problem, so we just plug that 17 in and we come out with 290 Kelvin for our first answer. If you look at the next problem, we see that we're trying to get to Celsius. Now, if you look at the equation, if we're adding to get to Kelvin, then to get to Celsius, we would subtract. So we take our 128 kelvins and we subtract that by 273. And when we subtract that, we get negative 145 degrees Celsius. And the very last thing we're going to cover today is something called STP. This stands for Standard Temperature and Pressure. This is the standard condition to measure gases. So as you can see, standard temperature is 0 degrees Celsius, also known as 273 Kelvin, and the standard pressure is 1 atm. And that's it. Thank you for watching.